Today we're going to be starting our AP Calculus A, B, and BC preview and review sessions. This first part will mostly be a review of pre-calculus. The second part will be a preview of AP Calculus AB, and the third part will be a preview of AP Calculus BC. So in this video, we're going to be covering mostly just basics of functions and then the different types of functions. That's basically all we need to know for calculus. If we have time at the end, we would also cover basics of calculus such as limits, rate of change, and area under the curve, just what you would learn in pre-calculus. Then tomorrow we'll get into derivatives and integrals, the calculus versions of them instead of the pre-calculus versions. And then the third day, we'll go into BC topics. So let's get started. We're going to start with functions. A function is basically defined to be a relation that has exactly one output for every input. So for example, if I had an input of 2, I can't have an output of both 3 and 5. Then it wouldn't be a function. So something like this would not be a function because it fails something called the vertical line test. The vertical line test is basically where you draw a vertical line and it can intersect that relation exactly once at each point. Of course, when you draw a vertical line here and it doesn't intersect at all, it still could be a function. So it's at most one point for every value in the x-axis. You can't go more than that. In this case, it goes twice, so this is not a function. On the other hand, this is, because for every point, it intersects, the vertical line intersects the graph exactly once. Function notation is f of x, and there are 5 main types of functions that we're going to be looking into today. Polynomial functions, rational functions, exponential functions, logarithmic functions, and trigonometric functions. But before we do that, we have to talk a bit more about the basics of functions. We'll be going over transformations, compositions, and inverse. So transformations of functions are basically either moving or reflecting a function. The main one is translations. So moving it horizontally h would use this, and vertically k would be this. So this is the formula for translation, or basically a physical movement of the graph. If you want to reflect it, you can put a negative sign. For example, f of negative x. Since you're doing negative x, if you had a graph that looks like this, you're basically flipping it over the y-axis because you're inversing all the x values. So if x was 2, it would become negative 2, and it'll be here instead of there. If x was 5, it would instead be negative 5, and that would be the new value. So it would look something like that. It would be reflected vertically. If you want to reflect it across the x-axis instead of across the y-axis, you would put a negative sign in front of the entire function. That would reflect it over the x-axis, what I like to think horizontally, because it's moving through the horizontal axis. So those are the main 2 transformations. Then we have compositions. So composition is basically we put one function as the input of another function. So if we had f of x and g of x, composition would be f of g of x. And of course, you have to check the domain of f of x and make sure it matches with the range of g of x. Otherwise, you're going to have to do some domain verification to make sure it works. But basically, compositions are important in calculus. For when we learn about derivatives, there's this one rule that works with composition of functions. Even regular functions like e to the power of 2x is actually a composition of 2 functions. Even 2x is technically composition. Of course, 2x plus 1 is a composition, and even x squared is a composition. Basically, almost every function is a composition. I would argue that just the function x isn't a composition, but x, 2x could be, because the outer function is 2x and the inner function is x. So that's a very simple example of a composition. But this is a bit more interesting. The outer function would most likely be e to the power of x. The inner function would be 2x. So you're replacing that x in the outer function with the 2x, the inner function, and you're getting this. Inverse function. So inverse function is basically something that undoes the first function. So if we had f of f inverse, so a composition of a function and its inverse, it will always be equal to x. And if you flip around the order too, f inverse of f of x would also be x, provided that f inverse of x is a function and exists. Sometimes you would have a graph that looks like this, and the inverse would be this. This is not a function because it fails the vertical line test. Now, how do we know it looks like this? There's a rule that says that the inverse of a function is always going to be the same function reflected over the line y equals x. So this is reflected like that. Now, I won't go into the details of inverse functions. For example, I won't go into how to find an inverse function because that's covered in pre-calculus, and this is just a brief review of pre-calculus. So I'm assuming you would know that from either algebra or pre-calculus. I'm just covering the topics that you would need to know, not going in depth into the topics. Okay, we're done with the basics of functions. We're moving on to different types of functions. Polynomial functions. So polynomial functions look something like that, for instance. Again, I won't go too deep into them, but you would need to know a lot about polynomial functions for calculus. You would need to know how to graph them. You will learn another way to graph them in calculus, but it is necessary for you to know how to graph them, how to find their roots, which is very important. An example I can give you is 3 times x minus 1 squared times x plus 4. How would we graph this? So assume we found the roots and factored it into this, because that's a long process and I won't have enough time to cover the entire process in this video. How would we graph it? The first step is to plot the roots, so 1 and negative 4. Then identify the degree, so that's a degree of 2. This is an unspoken degree of 1, so it's a degree of 3. A degree of 3 either goes like this or like this. That's the end behavior of a degree of 3. It's basically the end behavior of any odd degree, including a degree of 1 actually. Even degrees, I'll show you later, have a different end behavior, but which one of these is it? Well, based on the leading term, this is positive, so it would be this graph. If it was negative, it would be the other graph. So we know that it must start down here, and it goes through 4 because it's just a normal degree of 1. But when it gets to the root 1, it's a degree of 2, so it bounces off. That's what happens when you come across an even degreed root. If it's an odd one, it's a bit different, which I will show you in our next example. An odd one except 1. 1 you just go straight through, any even one you bounce off, and let me just show you the odd one. So let's say it's that same function. This time we'll put a negative in front of it. So it's x minus 1, and let's say to the power of 3 to demonstrate what an odd degree root looks like. It's also known as multiplicity, an odd multiplicity, times x plus 4. So for even functions, it either looks like that or like that. It's negative, so as you might assume, it's this, going towards negative infinity on both sides. So let's plot the roots again, 1 and negative 4. We know it must go downwards on this side. And it's, again, a multiplicity of 1, so it goes straight through. Now, what about for this? It won't bounce off and it won't go straight through either. It does go through, but not straight through. Instead, it curves a little bit here, and then it goes down. It's kind of like a wrinkle in that point, and then it goes through the x-axis and goes down. So that was just an example problem for polynomial functions, just to demonstrate what to do in each case. Moving on to rational functions. Rational functions, you're going to have to look at it in a slightly different way than polynomial functions. You're still going to need to find the roots, but there are other things you need to find, such as vertical asymptotes, holes, and horizontal asymptotes, aka the end behavior. So vertical asymptote, let's start with that. Let's say it's a function x minus 3 times x plus 1 over 2 times x plus 2 times x minus 3. Vertical asymptote is basically a term in the denominator. You have to look at a term in the denominator and make sure it doesn't cancel off. So in this case, x minus 3 and x minus 3 cancels off. So you might think that just doesn't matter, but it does matter, and we'll get to that in a little bit. But look for one that doesn't cancel off, so x plus 2 is the only one. The vertical asymptote would be what makes that term that equal to 0. So x equals negative 2. So this would be your vertical asymptote. What would be your hole? It's actually what is cancelled off. When it's cancelled off, it becomes a hole. So at x equals 3, there should be a hole of some sort. And the horizontal asymptote is based upon 3 factors, or has 3 cases based upon 1 factor. So the first case is, let me clear the screen to demonstrate the 3 cases. The first case is, let's say it's p of x over q of x. That's the function. If the degree of p of x is greater than the degree of r of x, or sorry, q of x, then you're going to go to either infinity or negative infinity, depending on the signs of the leading terms of both of these. Leading term, again, is the first term, so if you have like 2x squared plus 1, the leading term would be 2x squared. Second case is the opposite. The degree of p is less than the degree of q. In this case, it'll go towards 0, because there's more weightage in the denominator, so it'll go towards 0. And third case is when they're equal. This is the most interesting case, because it would always be equal to the ratio of the coefficients of the leading terms. So it'll be p of 1 over q of 1, the ratio of the coefficients of the leading terms. Now, what do I mean by that and 0? Well, I'm just saying that the horizontal asymptote is y equals 0 if it's case 2, and y equals p1 over q1 if it's case 3. If it's case 1, it just goes straight towards infinity like a polynomial function would. That's the most important thing about rational functions, because it actually has to do with calculus a little bit. When we talk about limits, this is going to be a big part of that as well. Then we have exponential and logarithmic functions. I'm going to group that into one. There's not much you need to know about exponential and logarithmic functions, how to graph them, of course, and that's the only thing I would be showing you in this case. So first, you would find the horizontal asymptote. Let's assume it's 1. Or sorry, it's 0. And this is for exponential functions first. And let's say the graph is something like 2 to the power of x. Very simple. The horizontal asymptote would be whatever is added on here. If it was plus 1, the horizontal asymptote would be 1. But in this case, it's 0. Now, you plot one point. Most likely going to be the y-intercept, unless there is a horizontal translation to the graph. In this case, there isn't. So it's going to be on the y-axis. We plug in x equals 0 and we get 1. So that's going to be our point. Second point, we plug in the point right next to that one. We plug in x equals 1. We get 2. And now we have enough to finish our graph. We know it must go towards infinity on this side and towards the horizontal asymptote on this side. So that's a simple way of solving or graphing an exponential function. Similarly, we can graph logarithmic functions, which are the inverse of exponential functions. So let's say log base 2 of x, for sake of similarity. we graph the vertical asymptote this time. It will be x equals 0 because there is no horizontal translation to it. Now, we plot the point, in this case it would be the x-intercept unless there's some vertical translation. In this case there's not. So we plug in y equals 0, so 0 is equal to this. What would x be? Well, that's 1 because 2 to the power of 0 will be 1. And we plot the point next to it, so we plug in x equals 2, we get 1 as our answer. So we get that, and now we graph it. Again, same thing, we know it must go towards the vertical asymptote and then towards infinity on this side. There's one last thing I want to mention about exponential and logarithmic equations and functions, and that's the fact that you can convert one to another. So if you have the function a to the power of x, and it's equal to some value b. So this is an equation. We can easily convert it to a logarithmic equation and back. The logarithmic equation would be log base a of b is equal to x. So you're finding to what power do you need to raise a to find b. So let me give you an example. Let's say it's log base 2 of 8, and you're trying to find out what it is. Well, you can convert it to the exponential form. You would take 2 to what power makes 8, and then you would go through the powers of 2 and you realize, oh, it's 3. Log base 2 of 8 is 3 because 2 to the power of 3 is 8. And finally, trigonometric functions. The only thing I'm going to talk about here is the transformations of the graph. So we have y, or f of x, but y equals a times sine. I'm going to talk about sine, but it's applicable to cosine as well. B times x minus h plus k. First things first, k is the midline. So that's the sort of the central line where the midpoint between the maximum and the minimum lies. Second thing, h is a horizontal translation, so moves the midpoint back and forth. Sine means that the central point is the midpoint, but if it was cosine, the central point would be the maximum point. There should be a plus or minus here. Since it's plus and sine, it would be central point is the midpoint followed by a maximum, so something like that. That's the central point followed by a maximum. If it was negative sign, it would be central point followed by a minimum. What if it was plus or minus cosine? Positive sign, you start with the maximum. Negative sign, you start with the minimum. Sorry, negative cosine, you start with the minimum. A is the amplitude, so that's the distance above the midline that the maximum is, which is also the same distance below the midline that the minimum is. And finally, we have b, which represents the period. B is always going to be equal to 2 pi over the period. The period is the distance between two maximum points or between two minimum points. And the larger the period, the more spread out the graph is. So this would be a larger period, while this would be a shorter period. That's all we have about reviewing functions in pre-calculus. Since we have extra time, we'll go into more of pre-calculus. Basically, the introduction to calculus that you receive in pre-calculus. First things first, limits. So a limit is basically when you approach a point, but it doesn't have to exist at that point. So it's best to see on a graph. Let's say you have a function like that, and you're approaching limit as x approaches 4. Now, this is just a normal graph, so it would exist at that point, and the limit is what each side approaches. One-sided limits are from one side, so either right or left. So let's say it was x to 4. Could either be plus or minus. If it's plus, it's coming from the right, and if it's minus, it's coming from the left. And if there's nothing there, it's the both-sided limit. This limit only exists if both one-sided limits exist and are equal to each other. So I'll give you a few examples of when this is not the case. So let's start with the easy one. This is just an easy limit that does exist. We have a piecewise function that looks something like that. So does this limit exist? No, because the right-hand limit goes here, but the left-hand limit goes to a different point, the two one-sided limits must be equal to each other, but they're not in this case, so the limit does not exist. Does does this limit exist? So we have this function, but there's a hole at this point. Does it exist? The function doesn't exist at that point, but the limit does, because we don't care about what's at that point. We care about whether it approaches that point. Both one-sided limits agree, so yes, there is a limit. What about the same scenario, but with the function defined up here? You might think that's a different scenario, but no, the graph still approaches this same point down here from both sides. It doesn't matter that the function is defined at a different point. It's still approaching that point from both sides. So the limit is still towards this point, not towards the point where the function is actually defined. That's simple introduction to limits. One more thing about limits is continuity. Continuity is unofficially defined when you can draw the graph without lifting your pencil. So this is continuity. I can draw this graph without lifting my pencil. But what happened in that previous example, when I had this hole here and this up here? Well, I had to lift my pencil to do that. So that's not continuous. There's a three-step process to finding continuity. The first step is that the function must exist at that point. So in this previous example we said, the function does exist at that point. It just exists up here. Second condition is that the limit must exist at that point. The limit does exist. We found that out before. Third criteria is that the limit and the function value must be the same. This is false because the function value is up here, but the limit is down here. So that's why this is not continuous. All three criteria must be true for it to be continuous. Rate of change. So there's two different types of rate of change. Average rate of change, or AROC, and instantaneous rate of change, or IROC. Each of them have their own formulas. For AROC, it's f of x plus h minus f of x over h. So this is basically using a graph. You have some function, you have some point x, and some point x plus h. So this is the slope of the secant line that goes through those 2 points. Secant line basically means it intersects the graph at 2 points. IROC is the slope of the tangent line. IROC, what you would do is you would basically put a limit in the front of this as h approaches 0. Not as x approaches anything, but as h approaches 0. So you're trying to make this point come closer to this point until there's only one point. The tangent line only intersects the curve at one point, which is why this is defined to be the slope of the tangent. So if it's a polynomial or rational functions, you can calculate a formula for this IROC, and you can just plug in values whenever you need to. And this formula is called the derivative. And we'll get more into that into the next section when we actually talk about the definition of a derivative. Hint, it looks extremely similar to this. In fact, it basically is this. This is the definition of the derivative. But we're not going to be able to use rules to calculate the derivative just yet. What we do at this stage is we plug in values for this, and we calculate it based on that. In calculus, there are rules you can use. The first few chapters of calculus, you would have to use this. It is going to take some time, but once you discover the rules about these, halfway through calculus approximately, you would understand how to do it much quicker. The final thing for this session is area under the curve. So when you have a curve and you want to find the area under it, in calculus you call that the integral. In pre-calculus you would just call that area under the curve. There are a few ways of finding it. RRAM is right rectangle area method. LRAM is left rectangle area method. MRAM is midpoint or mid rectangle area method. And finally we have unofficially named TEM, which is trapezoid area method. So I won't go into the details of each of these, but as you might imagine, there are different formulas for them. So RRAM. we have right endpoints. So I'm going to clear the frame to make it easier to see. Let's say we have this function from here to here. Right endpoint, meaning we have rectangles such that the right endpoint touches this graph. So like that. So obviously they have to be the same width, but in this case, it is just a rough sketch. There are formulas to find out this using summation notation, but I won't go into the formulas, I'll just go into the concepts. LREM is left rectangle, so left endpoint. That means that the left endpoint of the rectangle must touch the graph, so it's going to be going over. So the key difference between these two is that the different endpoints that touch the graph, which causes RREM to be an underestimate for graphs like these, and LREM to be an overestimate for graphs like these. On the other hand, if you have a graph that goes downwards like this, LREM is going to be an underestimate, as you can see, because that's the left endpoint touching. Sorry, I switched them around. This is the right endpoint touching. The previous example I showed you was the left endpoint touching. Sorry for that, but that first one I showed you is left endpoint. So I'll just show you them both on the screen to avoid confusion. So for something like this is right endpoint, and this is left endpoint, because that's the left endpoint that touches. So when this is called concave downwards because it's sort of like an upside down parabola that's going downwards. That's why this is different than the concave upwards we saw earlier when we had something like that. So when it's concave downwards, the right RREM basically is going to be an underestimate and LREM is going to be an overestimate. But when you have a concave up graph, RREM is going to be an overestimate and LREM is going to be an underestimate. The two others are MREM and trapezoid. Those are the most accurate of them. So if you're going to choose one, either choose MREM or trapezoid. So MREM is going to be when the midpoint intersects the graph. So something like that. Sorry, that's an endpoint intersecting. So something like that is MREM because the midpoint of it intersects. So as you can see, it goes over a bit, but it also goes under a bit. So it should sort of cancel out, not completely, but it should sort of cancel out a little bit. And finally, we have trapezoids, where you basically have both endpoints touching the graph because it's a trapezoid, not a rectangle. So you can do that. So I would say either this or MREM is the easiest and most effective ones. So LREM and RREM are just to get an understanding of area under the curve before moving on to this. Like I said before, these are called integrals in calculus, and you will learn formulas for them. Something that you will also learn most likely in pre-calculus is that this IRAC and this area under the curve are inverses of each other. The derivative and the antiderivative. The antiderivative powers the integral. So that's a bunch of terminology, but basically what I'm saying is when you calculate the derivative, you can undo that operation to calculate the integral. So that's a calculus topic, but you might or might not learn about that in pre-calculus. That's it for this session, this part 1. It's just a review of pre-calculus, and in the next part, we'll be going into AP Calculus AB. The third part, again, we'll be going into BC. So that's it for this